Hi.
Hi.
Over here.
All right, so Emily.
Yes.
You are going to be the only one joining me right now. Everybody else is going to watch later.
All right.
So we're going to make this lesson good, and they're going to get to watch afterwards, right? I linked in Edmodo 2 worksheets that I'd like you guys to work on.
Mm-hmm.
Those, I think, are really going to help you guys practice reading a phase diagram and practice naming the different phase changes, like when you're solidifying or when you are vaporizing or condensing. That's the point of those worksheets, is to help you practice that.
Yeah.
So did you have a chance to look over that section in the chapter?
Which one? Is that the very last one? 12.3?
Yeah, the very last one.
Yeah, I'm pretty sure I have notes on that and everything.
Okay, so what I'm going to do, Emily, is I'm going to screen share, and if you're able to look at the worksheets while I do this, if you're able to have them, that'd be fine. If not, you might want to print them out later if you're able, or just work on them through my screen and write them down on a piece of paper. But I'm going to screen share and go to those worksheets. I have them pulled up. Okay.
Yeah.
Now, all right. Screen share is going to mess up the camera for a little bit, so bear with. All right, so Emily, can you see the screen?
Yes, I can.
All right, so do you see how here, these are the 2 links to the 2 worksheets? So
yes.
you can click on either of those later to get to them. This is also for Jordan and Emily. When they get on this and watch this later, you guys have to do these 2 worksheets. They're right here in the newsfeed, okay?
Okay.
So I have already pulled these up. Here's the first one. The first one is the phase diagram worksheet, and this is going to look very similar to the worksheet, the phase diagram on page 429 in your textbook.
Mm-hmm.
You have to be able to read a phase diagram and label a phase diagram and intelligently answer questions from a phase diagram. Now, because we're not counting this particular test as a test grade, it's more for your final exam. You will have a phase diagram on that, and you will have to answer similar questions to this, okay?
Okay.
I'm also going to make these worksheets be due as, I'm going to count them as a quiz grade, the 2 worksheets together. Now, this particular worksheet does have the answers at the bottom, so it's not like I'm trying to trick you. If you don't know, you can check. And after you take it, you can check to see your answers. But I do want you to have the exposure to working with this, okay? So notice how it says, at standard temperature and pressure, bromine is a red liquid. Bromine sublimes when the temperature is negative 25 degrees Celsius and the pressure is 101.3 kilopascals, which is a unit of kilopascals, my corny joke, Pascal. It's a unit of pressure.
Okay.
All right. So this is the phase diagram, and notice that you see on the x-axis, what's down here?
Down where?
Watch the mouse. Do you see the mouse?
Temperature?
Yeah. And then what's here on the y-axis?
Pressure.
Pressure. So see how it's comparing temperature and pressure, and this is what state of matter bromine will be at. Now, in your book, look and find what's the first section, the section that is always closest to your y-axis, right here where my mouse is. What is this section always? It is a solid. You're correct. The middle section in the middle of the y is always what?
A liquid.
Good. And then the section over here is always?
Vapor.
Good. It's a vapor or a gas. Now, you do want to know the difference between those two terms. Think about this, though. We say carbon dioxide gas, and we say water vapor. Can you think of why the difference is there?
Water vaporizes. And
I'll give you a hint. What is water, solid, liquid, or gas at room temperature?
It's liquid.
It's liquid. What is carbon dioxide at room temperature? Solid, liquid, or gas?
A gas.
Gas. That is why you say water vapor. It's distinguishing that it normally would be a liquid at room temperature, but it is right now a gas. So that's why we say vapor. If you have something that is normally a solid or a liquid at room temperature, it's called a vapor when it's in the gas form. So that's it. So notice that we already actually answered question section 1. It said label each region on the graph as solid, liquid, or gas. So you already did that for us on this. Now this is important. It says label the triple point, normal melting point, and normal boiling point on the graph and estimate their values in the space below. So let's start with, where is the triple point on here? Do you know this? Do you know which point that is?
No, I do not.
Okay, let me help you by identifying a few things. First off, this line right here, anywhere on this line, what we're saying is if I'm right on the line, like where the cursor is right now, right here, I am at that temperature and that pressure, like let's say I'm right here, that would be about negative 9 degrees Celsius and 60 kilopascals, right? That would mean that at that temperature and pressure, I'm changing from a liquid to a solid or from a solid to a liquid. This line is the change of state between a liquid and a solid. This line, all the way from right here, all the way up, is the change of state from a liquid to a gas. So if you cross the line, you're turning from a liquid, like if you start here and you go over here, you're turning from a liquid to a gas, so you are vaporizing. If you start over here and go this way, back from a gas to a liquid, you are condensing. Same thing down here. If you cross this line, you're turning from a solid to a gas or a gas to a solid, which solid to a gas is sublimation. Remember, because you start with an S, and so it's sublimation, SS. If you start over here as a gas and you cross the line this way, you're going from a gas to a solid. That would be deposition.
Okay.
So which point on these 3 lines do you think all 3 phase, like if I'm right on this dot right here, I'm a solid and a liquid at the same time. If I'm on this dot, I'm a gas and a liquid. If I'm on this dot, I'm a gas and a liquid. See? So which dot on this, which dot do you think is going to have all 3 phases of matter at the same time?
The one by negative 10.
The one by negative 10 right here, this guy. That is correct. That is called the triple point, and it's special because it's a place where all 3 states of matter exist at the same time. So literally, if you had a cup and you put bromine in it, and you've made it be about negative 9 degrees Celsius and about, I would say, maybe 5 kilopascals, if it's at that temperature and that pressure, it would literally be boiling, freezing, condensing, solidifying. It would be doing every single phase change at the same time. So it's pretty cool.
Mhm.
All right, so that's this one, the triple point. Where do you think the normal boiling point is and the normal melting point?
So they have to be on the dots, or are we talking degrees?
Yeah, for those, they'll be on the dots. So think for me, first tell me which dot would be melting. What phase change is that? We start with a what and we end with which
Solid
state
to
of matter?
liquid.
Solid to liquid, good. So find the line that's separating solids and liquids.
Mm-hmm. Would that be the top?
It's one of the tops, good. Now is it this top one or this top one?
The first one.
The first one, this one. I know, these should be labeled A, B, C, or D.
Yeah.
Sorry about that. So this is the normal melting point, which is good. So you can estimate that and write it down. And then, what was the other one? Normal boiling point, right? Okay, so where is it going to go from a solid to a liquid? That's not, we just did that. I'm sorry. I said the wrong thing. What was that again? Boiling point? Boiling is going from a liquid to a gas. So where's that going to be? This dot?
Yeah.
This dot? This dot? Let's go A.
Did we just do that one though?
C or D? What?
Did we just do that one though?
Which one is?
The boiling point is the first dot.
Boiling?
That's what
boiling's going from a liquid to vapor. It can't be this one.
Oh, I'm sorry. You said melting. We already did melting. Now we're
yes.
I'm sorry. I was confused. I thought we were talking about boiling. I mean melting. Okay, so boiling. Would that be that one right there?
It's this guy right here. Yep. There you go. All right. So you're going to label the lines, and you can do A, B, C, but you see how you're going to label A for the line that goes equilibrium between solids and liquids. So where are you going to get solid and liquid? And I'm going to say, which line is it? Is it this line or this line or this little line right here?
The first line.
That's right. Good. So this is the line between solids and liquids. Now, it asks, label B for the one that gives the between a liquid and a vapor. So is it this one or this one right here?
Liquid and a vapor would be the second one.
The second one right here?
No, the other second one.
This guy.
Yes, the long one.
All right, good. And then this one would be the last one between a solid and a
vapor.
Vapor. So that's correct. Yep. All right, and let's see. Describe how the melting point of bromine changes with the external pressure. Based on the slope of the melting point curve on the phase diagram, would you characterize the solid phase of bromine as more dense or less dense than the liquid phase? So let's see. Melting point along this line, right?
Mm-hmm.
So as you are increasing your pressure, what do you think? Are you melting more or less?
We're melting more as we increase pressure, I'm assuming.
Yeah. I'm not a fan of that question. Let's go down and see what they actually say. Hang on. Da-da-da-da. 1, 2, 3. There. The melting point curve leans slightly to the right, has a positive slope. And it says, so as it increases, yeah. So higher pressure, higher density. Yep, you were right. Kind of figured, but I didn't know exactly what they were looking for on that one.
Yeah.
All right. I'm going to actually skip these. You can go back and label them at the end. But do you understand the idea behind these?
Yeah, it makes a lot of sense.
Okay. So this particular diagram, so this one is 10 through 15. You're going to use this mysterious compound X, and it labels solid, liquid, gas for you. And then they're going to ask you questions about that. Do you think that this, and they also have another one for 16 through 22, and it's solid, liquid, gas, and you have the critical point and the triple point. Oh, we didn't mention the critical point yet. At the end of the line between a vapor and a gas, the critical point is the place where even if you increase the, hang on, let me make sure that I say the right thing. Even if you increase the temperature after that, it can't be a liquid anymore. So if it's going to have to be a superheated gas at that point, since it's no longer able to be a liquid. The atoms are just too excited.
Okay.
All right. Do you have any questions about this one, though? This particular worksheet, I think that once we looked at the phase diagram and you labeled it correctly, that's the main ideas behind this one.
Yeah, I think the other ones are pretty self-explanatory.
Okay, and there's an answer key, so if you do have problems with it, you can always look at that, but otherwise, you can ask me. Just email me or ask me on Sunday.
Okay.
All right. This is the other worksheet. And let me scroll to the top. This is actually nice because it does kind of tie in with some of the things that you're doing on your project. Mm-hmm. So it has a summary of the kinetic molecular theory and the states of matter and how they compare to each other. Mm-hmm. You'll have to label melting, freezing, evaporation, condensation, sublimation, and deposition, which is great because those are the phase changes that we need to know. Mm-hmm. So that I'm not going to go over with you. You can look that up.
Yeah.
This is our solid to liquid to gas. We're labeling now, just like we did up here. We're going, when we go from a solid to a liquid, what's that called? And you write it down on here.
Okay.
When we go from a liquid back to a solid, what's that called? And you write it down on this line. So that doesn't, I don't think that makes kind of just makes sense. So I'm going to keep going. This is the one I want to talk about. It's a little large to fit on my screen. So you see the phase change diagram. It's just like the other one, only you have your energy. As you go this way, you increase energy. And as you go up this one, you increase in temperature. So what they do is they have the solid form here, lowest energy, lowest temperature, right? Mm-hmm. Then you have your liquid, little bit more energy, little bit more temperature, right? Mm-hmm. And then your gas is up here, highest energy, highest temperature. Mm-hmm. So these are the same idea. You're labeling your phase changes from a solid to a liquid. Label it right here on this line number 9.
Okay.
From a liquid to a gas, you label it here on line 11. And when you go from a gas back to a liquid, label that right here, and so on and so forth. Does that make sense?
Yeah, it does make sense.
And then the one where it goes directly and skips the liquid phase, that's down here. But they didn't do the reverse, so you won't have the reverse of that. Just the one where you go from a solid directly to a liquid, or to a gas, I'm sorry.
Okay.
All right. This is going to ask you some questions about the phase diagram. I want to ask you and focus in on this level area. With this, remember that this is energy, right? Mm-hmm. So when we are heating up a solid, let's picture like an ice cube, and you take it out of the freezer and put it on the counter. Mm-hmm. What's going to start happening to the molecules inside of that ice cube as they're on the counter?
They're going to melt?
Yeah, but think of the molecules. Do they stay locked in a rigid structure? Do they? What happens to them?
Gaining energy.
They're going to start gaining energy. Good. As they gain energy, they're going to start to move more, right? So they start sliding past each other a little bit more or vibrating a little harder until they have enough energy to break free from the crystal lattice and start flowing back and forth. That's when it turns into a liquid. So the solid has to increase in temperature, increase until it reaches the place where it starts to melt. Mm-hmm. At that place, as soon as it starts to melt, every bit of it, the solid, is absorbing energy, and all of it is converting from a solid to a liquid. While that phase change is occurring, the solid and the liquid mixture won't gain any more energy. All of the energy is being used to turn the solid back into a liquid. You know, so it's not gonna, like, the liquid will stay the same temperature the whole time until it's completely melted. So do you see how at this point we leveled off on the energy or the temperature?
Yeah.
As we're increasing the energy, we don't have any higher temperature. For water, this is actually happening at 0 degrees Celsius. Mm-hmm. At 0 degrees Celsius, the ice will start to melt. And then until all of that ice is melted, it's going to stay at 0 degrees Celsius. And it'll just, any energy that's absorbed is going to be sent to the ice cube to turn it into water. Then, once we have that 0 degrees Celsius, once it's all liquid again, we start heating it up again, and the temperature can start to rise now. As it's getting energy, it'll rise until 100 degrees Celsius. Once it reaches 100 degrees Celsius, what starts to happen to the molecules?
They vibrate even more and they turn into a gas.
Good. They're going to start moving more and more and more until they turn into a gas and they start escaping. And that's called vaporization. That's when it's turning into a vapor. Mm-hmm. At that point, it's at 100 degrees Celsius. The temperature of the water will not increase at all until every bit of the liquid is gone and it's all turned into a gas. And then if you're still adding energy into the gas, it'll start moving faster and gaining temperature and increasing. But here, this will be a plateau again, where until it completely changes, it's going to stay at the same temperature.
Yeah.
The exact same thing happens only in reverse when you are cooling things down. So again, if you take a gas and you start to cool it down, cool it down, cool it down, cool it down, at 100 degrees Celsius, it's going to stop changing temperature and start condensing. And until every bit of that water vapor has turned back into liquid water, it's not going to change temperature. Then you can still cool it, and it goes from 100 degrees all the way down to 0. Once it reaches 0 degrees Celsius, what's going to happen?
Is it going to turn back into ice?
It is. It's going to start turning back into ice. And so look, while it's freezing, is it able to change its temperature?
While it's freezing?
While it's freezing. Well, you still have solid and a liquid in the container.
It's going to keep changing and get colder.
It's going to keep changing to a solid, but will its temperature go lower?
No.
No. The temperature plateaus at 0 degrees until every bit of it is solid. Mm-hmm. And then, you know how you have your ice in your freezer?
Yeah.
After all of the water has turned to ice, it can start getting colder and getting below 0 degrees Celsius.
Mm-hmm.
So that is what those plateaus mean. Does that part make sense?
Yeah, that does make sense.
Okay, so this is going to be like a story problem. They're asking you to as you read this, you fill in A, B, C, or, you fill in those lines into this story.
Yeah.
And that's it. Let's see. I think that these are the answers. They do have the answer key to this one as well. So both of these worksheets have the answers. Mm-hmm. The main thing is I just want you guys to work on them. I think I hear Emily. Hang on. I have to get back to the screen and stop screen sharing. Stop screen sharing. Cancel. Okay, we're back. No, it's just you. Okay.
Yeah.
Sorry. Do you have any questions? Really, I don't think that this was a hard chapter. It's just I wanted to point out the phase diagram because you guys haven't probably seen that, whereas you're really familiar with freezing and, you've done phase changes before in probably many different science classes, but you probably haven't had to understand what a phase diagram looks like and have to answer questions about it.
On the Edmodo thing. So explaining that was a big help. That's
okay. Good. All right, so that's the only thing I wanted to do in this extra lesson. It didn't take long at all, but I hope it helped. And I will see you on Tuesday.
All right, thank you so much for taking your time to do this.
No problem. I am going to actually post before I leave the homework for Tuesday. I am going to keep going on to chapter 12 while you guys are working on your project. I just wanted to give you a little bit of extra time for the project because it is a big project. It's a lot of 20 slides. So I figured 2 weekends would be helpful, and I hope you are able to take advantage of that.
Yes.
Oh, I didn't check my email. What was your question about that?
What email?
You said you asked me a question. I think I saw that on Edpuzzle.
That's probably the other Emily, because she asked you.
Okay, probably the other Emily then. All right, never mind. I'll have to read my emails.
Okay, all right.
All right, bye.